In this second video lecture about context-free grammars, we're going to talk about this problem of ambiguity in a context-free grammar. So we've seen this kind of grammar before in the first video lecture. The only difference here is that instead of multiplication, I'm using division just for a change. And this grammar here, its start symbol is a E. There's only one non-terminal, and you can see that it does subtraction and division, and you can put brackets around it using R3, right? So if I have this input string over here, then I want to look at that input string and see, can I get two different parse trees for that input string? If I can, then this grammar is ambiguous. In fact, grammar is ambiguous if any string, if even one string in its language has two different parse trees, that means the grammar is ambiguous. So let's consider starting from the start symbol E and then choosing. I can't really choose this one because there is no parenthesis in this input. So what I care about is exactly processing this input string. I don't care about any other input string right now, right? I just care about that one. So whenever I produce a parse tree, it better only have this input string, ID minus ID divided by ID, on the leaf nodes of the tree. Otherwise, it doesn't count as a tree, as a parse tree for this input, right? So this one is out. And this one, I guess, is out as well because I need to get some operators in there, right? I cannot just get one ID. So the choice here is choice between R1 and R2. So it looks like I could choose R1 or I could choose R2. If I choose R2 first, then I get this parse tree over here because E gets expanded by E divided by E. And then this E needs to recognize the ID minus ID part of the input string. And you can see that this gets you the wrong precedence because it does the subtraction first instead of the division. If I choose R1 first, then I would choose E goes to E minus E first, and then I choose R2 over here where the division happens. So notice that this one corresponds to our intuition about division having precedence over subtraction, and that notion of precedence simply means I prefer this parse tree and I disprefer this parse tree over here. Notice also that higher precedence means that the rule that you want to pick that has higher precedence occurs lower down in the tree, right? If it occurs higher up in the tree, then it seems to have lower precedence. Higher precedence, you want it lower down in the tree, as you can see here. So grammar is ambiguous if there's more than one parse tree for an input, and there is essentially you can say that more formally as having more than one leftmost or more than one rightmost derivation. So if an input string has more than one leftmost derivation, then the grammar is ambiguous. And ambiguity is not really something we want when we're talking about programming languages, because an ambiguous grammar for a programming language is really not something we want. It's dangerous. It leaves the meaning of the programs ill-defined because there might be more than one way of doing code generation if it's ambiguous. We want our programs to mean one thing. Like when we compile it, it should run one program, not some arbitrary program which is ambiguous, in which we have no control. So we really don't want ambiguous programs, and therefore we want a grammar for programming languages to be unambiguous. Unfortunately, it's undecidable. What that means is that there is no valid program or algorithm that you can write to check whether a given context-free grammar is ambiguous. It's shown by equivalence to other problems like the halting problem that are undecidable, and so it can't be automated, right? So you can't just say I'll write an ambiguous context-free grammar and then convert it into an unambiguous one. Some context-free languages are inherently ambiguous in the sense that it's impossible to write an unambiguous context-free grammar for those context-free languages. So if some inputs are guaranteed to have two different parse trees, and you can't do anything about it. Luckily, this case is pathological and we can sort of work around it. We don't have to write, programming languages don't really have this kind of inherently ambiguous property. And we're going to get around this by making sure that we make our context-free grammars unambiguous by design, or at least we can use some kind of operation like precedence or associativity to make sure that the grammar is unambiguous. So these are things that you have to keep in mind when you use a context-free grammar to define the syntax of a programming language. So when we want to handle ambiguity, we can rewrite the grammar to make it unambiguous. Notice that we have to do this by hand because there's no algorithm that can do it for us. Or we could augment the parser by enforcing precedence and associativity. So this first point is what we'll cover in this lecture, and then this particular way of doing it by augmenting the parser we'll cover later on in a future video lecture. So let's consider the original ambiguous grammar. It's the same grammar we saw before. You have subtraction, you have division, parentheses, and identifier. It has 4 rules. How do we change this grammar to get the one tree, a preferred tree for the input string, the same input string we saw before, which is id minus id divided by id. So we're just focusing on this one string as an example. So what we want is to somehow impose precedence that division should happen before subtraction. So if I have this original ambiguous grammar, I want to push the division to be lower down in the tree as we saw before. And what we can do is use different non-terminals for each precedence level. So we start from the lowest level. The lowest level starts here, which is the parentheses. We call this the rules that start with the left-hand side of f, which is short for a factor. And then the next level up, we have the division, which has higher precedence than subtraction. So we want to make sure it occurs lower down in the tree. And so this part over here, these two productions, t goes to t divided by t and t goes to f. These two productions are going to handle division at a higher precedence than subtraction. We'll call that a term. And then finally we have the expression level, which is sort of what the original grammar had, was just an expression level, right? And here we have subtraction, which is the lowest precedence, so it occurs higher up in the tree. So if you look at this input now, id minus id divided by id, I start from the start symbol, which is e, and then I have to expand e. So I can either choose e goes to t or e goes to e minus e. So I can choose e goes to e minus e first, because otherwise I can't get the subtraction operator at all. And then I expand the e goes to t, so I chose this one. And then I choose this one, t goes to f, and then I choose f goes to id, right? So in this case, we have to go to this whole chain of productions to get to an id. And then I take e goes to t, so I have to take this step here in order to get a t. And now I can use the t goes to t divided by t rule. And then I can just get the id by expanding those t's to go to f, and then goes to id. Notice how by changing the non-terminals, I force the division to go lower down in the tree, and thereby you can ensure that division has higher precedence. So try to write down 2 leftmost derivations for the input string id minus id minus id using the same grammar. So you can see that this grammar is actually ambiguous because it has 2 leftmost derivations for this particular input string. So try and write down those 2 leftmost derivations. So here's the grammar that captures operator precedence. The previous question from the previous slide already sort of gave it away a little bit. This grammar is not actually unambiguous because there is an input string, an input sequence of tokens for which it produces 2 different parse trees. So if you take 2 subtractions, one after the other, this layer of expression, term, and factor, they don't really help with two subtractions, because the two subtractions are both going to be handled with this rule. And if you look at that rule, you can see that I have two different ways. I can either expand this E first or this E. Either one will get me the same input string, ID minus ID minus ID. So there are two different ways to derive the same input string, therefore it's ambiguous. So if you look at the structure of this tree, this is has dots here because it's supposed to go from E goes to T, T goes to F, and then F goes to ID. And to save space, I just use dots to represent that. The overall structure of the tree is what matters. So you have E minus E. You can have this left side be undergo subtraction first, or you can have the right side undergo subtraction first, because both are valid according to this grammar. So the grammar is ambiguous. We know how to solve this by saying that one of these trees is what we prefer, right? So we prefer it to be left associatives, let's say. So this is preferred and this is dispreferred. Now we want to use the same idea and allow one tree by changing the grammar, making the grammar unambiguous by modifying the non-terminals. So we want to group these operations from left to right. So before we go into how to do that, let's define some terms. So we say that a grammar is recursive in some non-terminal x if I have some sequence of derivation steps that gives me the same non-terminal after some sequence of steps. So basically, you end up back with the same non-terminal, right? So we saw examples of this where the while loop was sort of nested inside a if loop, if statement, and then inside the while loop there might be an if statement again. So essentially, what you're doing is recursively generating nesting structures in programs. So this is called recursion in the grammar. And all that means is that the same non-terminal occurs after you expand this non-terminal x. You keep expanding it, eventually you come back to x, so you can expand it again. So notice that I can take this whole sequence and repeat it on this symbol x, right? So that's why it's called recursion. It's left recursive if after one or more steps you get this x, so it's recursive. But furthermore, it happens to be the leftmost non-terminal here is the same one you started off with, right? So this is called left recursion because you end up with a symbol that's the leftmost in this derivation. Similarly, a grammar is right recursive in x if you start off with x and you end up with a sequence of symbols that ends with x, or x is the rightmost symbol in this sequence. So what happens here is I can again take this sequence of derivation and apply it to this x and expand it. So notice that this expands leftward and this expands rightward. So left recursion fills more material in on the left corner, and the right recursion fills in more material on the right corner. So it's sort of building a tree that is left branching in left recursive cases and right branching in right recursive cases. So we'll look at some examples. So if you want to fix associativity, what we want to do is make sure that if I have ID minus ID minus ID, I want to make sure that I bracket this one first and then I do this second. So the way that we're going to ensure that is by, instead of doing E minus E, we're going to do E minus T here. So E minus T guarantees that if I want to do two subtractions one after the other, I need to do it using left recursion only, rather than having a choice between left recursion and right recursion. So if you remember here, I have a choice. I can do either left recursion or right recursion. But here I'm taking away that choice and I'm saying you can only do left recursion because we want left associativity. If you wanted to enforce right associativity, you would use right recursion. So notice that the main change here is I've changed from this E have eliminated that and using T instead of E there forces a bracketing that looks like this. So using this context-free grammar to check that you're following along, write down all the possible leftmost derivations for each of these 3 strings here, input strings, just to figure out whether how is it dealing with this ambiguity. So let's look at an example using this grammar that is unambiguous both in terms of precedence and associativity. So if you have division and subtraction or addition and multiplication, you can correctly use the right precedence. And if you have multiple operators that are the same, like multiple additions, then it will also pick one tree, the left associative tree, in order to make it unambiguous. So you get only one parse tree for every input string. So if my input is ID plus ID times ID, then I would start off with this. I have to have the plus be generated from the E rule, right? So I have to get this plus by using the E rule. So E goes to E plus T, and then I would get the ID. So thus I would get ID plus, so far I've got an ID and I've got an plus. Now I want to get this ID times ID. So I would do T times F by using this rule. And then I would get the ID for the first sort of argument to the multiplication is this one. And then I would get F goes to ID. Is this unambiguous though? So you should check whether it is unambiguous or not. Check for this input string. And you will see that there actually is 2 different ways to use this grammar. So this F goes to minus E rule, there's something fishy about that rule here. So compare it with a different rule, which is F goes to minus F instead of F goes to minus E here, and see the difference for this input string. And you can see that this original grammar, it says it's unambiguous, but it's actually not really unambiguous. That was a trick to see if you could catch this case over here. Let's look at the so-called dangling else ambiguity. So in all modern programming languages, when you have an if statement, you have a condition and usually have curly brackets that specifies exactly where the if statement block starts and ends. And if I have an else, I also have a curly bracket that shows exactly where the scope starts and ends. If I have a nested if statement here with an else, I know that it has to be completely inside this block. What if you did not have these curly brackets in your syntax of your programming language? You can see that it makes it ambiguous, right? I don't know whether the else goes with the first if, the closest if, or the farther if. It could be either one. So let's consider an input like if E1, then if E2, then E3, else E4. So notice that this else has 2 possible ifs that it can go with. And again, we are assuming that we don't have any curly brackets. So this else is perfectly reasonable to use. Let's call R1 and do R1 first, and then do R2 to get if expression then statement over here in the lower part. And R1 puts this else with the first if. So if I was to draw the dependency over here, then it would be taking this else and matching it up with this if. But there is another possible way to do this. I can do R2 first and then R1, in which case what happens is that this else statement is going to match with this if. So there's 2 possible ways to derive this input string, to give a parse tree for this input string. That's why this grammar is ambiguous. So when we want to deal with this dangling else ambiguity, what we need to do is provide some kind of rule. The rule we had for arithmetic expressions was that we used to use precedence and associativity. What can we do for ambiguous sort of grammars like this one, which is dealing with structures like if then else structures. So a reasonable thing to say is that the else matches the closest unmatched then. It's kind of it's not a precedence rule, but it's a rule that can be used to make the grammar unambiguous, right? Because it picks one tree over the other. One way to do this is, and this is not a trivial way to do it, because it takes quite a bit of thought to get to this unambiguous grammar. I'm just going to show you how you can write an unambiguous grammar for this, assuming this kind of disambiguation rule. So the first thing we do is split up the statements into two different parts. One is a match statement, in which case you always have the else matched to a particular if statement. So all the then are matched in this one. And an unmatched statement, because not every if statement needs an else. So sometimes you can just have if expression then statement. So that's captured by this part over here, which is a potentially unmatched statement. Okay, so what do these look like? A match statement, like we said, always has an else and then and an if all together. It never has this particular rule is not in a match statement. And notice that inside a match statement, you can only have other matched statements. So each one of these is also guaranteed to have the else matched up with the if. So if this, if I expand this out and I have an if there, it will have an else as well. Similarly for this one, since it's a matched statement, it always has an if with its else. Okay, so what does the unmatched statement look like? An unmatched statement captures the case without an else. And then if it does have an else, then what it makes sure is that the part which is before the else is always using a match statement, so that it always has a matching if else inside. And whenever it has an else here, it matches to an F. It's always the case that that's going to happen with an unmatched statement. So notice that in this unmatched statement, I cannot have an else. So I cannot have a dangling else in this unmatched statement. It can only happen if I take this unmatched statement and then use this rule to expand it. I would get an if, else, and then an unmatched statement further. So I would always, even in this case, if I expanded it using this rule, I would still get an if else that's matched. So it can be quite difficult to actually come up with an unambiguous grammar. It took quite some time to figure out that this is the right way, like this approach is the right way to create an unambiguous grammar. Nowadays, of course, in most modern programming languages, like I said, people just enforce the unambiguous grammar by saying you must have these curly brackets that specify the scope. But it is possible to use this heuristic or rule that makes it unambiguous and write an unambiguous grammar for the dangling else ambiguity case. So what I would like you to do is to check that previous unambiguous grammar with the following inputs and check whether for each one of these inputs, do you get one parse tree for each of these cases, or do any of them get multiple parse trees? If any of them get multiple parse trees, you know that the grammar is not unambiguous, right? Because if it has multiple parse trees, then it's an ambiguous grammar. So the claim is that it should get only one parse tree for each. But this is a good exercise for you to follow how to take this input through the grammar, and then it's a much longer input, pass it through the grammar, see if you can get a parse tree. And then finally, this one is like quite the beast. It's quite long, but it's going to be helpful to you to work it out, to get practice and get familiar with how context-free grammars work and how ambiguity works in context-free grammars. So when we define a grammar for a programming language, we can actually tell the parser what to do about these ambiguous grammars. You might say, well, why not just make it unambiguous? So by any means necessary, make it an unambiguous grammar. Well, sometimes a potentially ambiguous grammar can be useful because often the grammar doesn't have as many non-terminals. It's much easier to read for humans. But if you do use those more ambiguous grammars, you do need some kind of disambiguation mechanism like precedence and associativity. So most modern compiler tools for generating a parser will allow you to specify precedence and associativity. So instead of rewriting the grammar, we sort of have these precedence and associativity declarations, and these declarations are used by the parser generator, like Yak, for example, to disambiguate the grammar so that for every input you only get one parse tree. And we know which one is going to be because we're going to define it using precedence and associativity rules. So let's consider this very simple grammar. E goes to E minus E, or int. And int here just stands for an integer constant, not the integer type. So if I give it this input, you can see that it is ambiguous because I can either derive it using left recursion or right recursion. So these are the two different trees I would get. If I wanted it to be left associative, then I could actually tell Yak a very simple declaration like %left minus, which says that whenever I have minus here and I'm going to use this rule E minus E, make sure that I prefer the left associative one, which is this one, and disprefer the right associative one. So by using this declaration, I can tell Yak that I want it to be left associative. We'll see later how it can be implemented in Yak, but for now, to use it is very straightforward, right? Any user knows what precedence and associativity rules they want, so they can just write it down, tell the parser generator what they want by using this kind of declaration. Now let's look at precedence declaration. So consider this grammar, which has subtraction and division. And again, this integer here is supposed to stand for an integer constant. So it's ambiguous, so it has two different parse trees, right? Because we can either choose this one first or choose this one first. And what we really want is that we want our division to happen first. So we want this division happening before the subtraction. So division should have higher precedence than subtraction. And so I can say that I have another declaration here which says %left for division, which means that if I have id, or sorry, in this case, int divided by int divided by int, so three integer constants like 3 divided by 5 divided by 7, then I would group this in this fashion, right? Left associative for division as well, but it also has the order between division and subtraction, which tells me the precedence. So we can get rid of this dispreferred tree by using this precedence declaration, and it's just in the order you provided. So the lowest one has the highest priority, and the priority gets lower as you go up. So the highest priority is at the bottom, and then as you go up, you get lower. So high to low precedence.